after having studied the various properties of the Fourier transforms, let us now discuss how this theory can be applied to the analysis of systems. So, we will like to see how the Fourier transform theory can be used to find out the output of a system corresponding to various types of inputs. So, in the system terminology, if we represent the input and the output as x of t and y of t respectively, this is a linear continuous constant parameter system. In general, the input and output are related by a differential equation of this type dmy dtm plus a m minus 1 dm minus 1 y dtm minus 1 etcetera plus a naught y, that is equal to d n x dtn plus b n minus 1 dn minus 1 x by dt n minus 1 etcetera plus b naught x. This is the type of differential equation that in general you have for a single input single output constant parameter time invariant linear continuous time system. In such a system, if the input x is e to the power of say s t, then the forced response will be obtained by taking the instead of the d operator, you multiply equivalent of s operator, that will be equal to s to the power of n b n minus 1 s to the power of n minus 1 etcetera plus b naught divided by a m s m plus a m minus 1 s m minus 1 plus a naught multiplied by e to the power of s t, where this is the input and this is the corresponding output. This is the forced response or the particular integral solution of this differential equation. And this we observed is called the system function h of s. We are in particular interested in the system function evaluated when s is equal to j omega. So, if this is h of s, h of j omega is the frequency response function also called system function. So, often this is also by itself called system function, and it is this particular function which we will make use of in the Fourier transform applications to systems. Now, let us see the implications of the system function. 1. Suppose the input is e to the power of j omega t, then this is x t. It means the forced response E f y f of t, the particular integral solution of this differential equation, the forced response will be h of j omega multiplied by e to the power of j omega t. That means h of j omega multiplied by x of t. So, the forced response and the input are related by the multiplicative constant h of j omega, which is independent of time. That is why I am calling this a constant. A particular case, if the input is a sinusoid, then the output phasor and the input phasor, these are phasors, whether the voltages or currents as the case may be in the case of an electrical network, or in terms of general systems you can define the phases in the same manner. Both are sinusoidal functions of time. This is given by h of j omega once again, where a sinusoid of frequency omega. So, under steady state the output sinusoid and the input sinusoid, their phases are related by this h of j omega. So, that is the significance of the system function h of j omega. If you have an input x t which is an exponential function e to the power of j omega t, then the forced response y of t is h of j omega multiplied by e to the power of j omega t or x t. This after all both are related to each other. And it is this property which we are going to make use of in our Fourier transform theory, because we are breaking up any given x of t as the summation, infinite summation of time functions of this type. So, this is what we really want to make use of. So, in a general case, we have a x of t is related to its Fourier transform as 1 over 2 pi minus infinity to plus infinity of x j omega e to the power of j omega t d omega. You recall that this integral arose from considering a number of elementary signals of coefficient density x j omega lasting from minus infinity to plus infinity. So, in fact, we said this is the limit as delta omega goes to 0 of a huge lot of summation of a huge lot of terms x j omega delta omega over 2 pi, this being the coefficient density and delta omega over 2 pi being the width of the elementary slice of the spectrum that we are taking. This is the coefficient and this is the function of time which it takes, and if you take all such signals, add them up, you get this x of t, that is the general input. So, if we have a general input x t, it can be thought of as a summation of elementary signals of this type, each with an amplitude like this, and this omega running from plus infinity to minus infinity. Now, from this you conclude, since if it is e to the power of j omega t, the forced response is h of j omega times e to the power of j omega t. All we are doing is instead of e to the power of j omega t, you have a certain amplitude, certain coefficient. So, the forced response will be x j omega delta omega over 2 pi times h of j omega e to the power of j omega. And once again here also we have that limit as delta. This is the response for a single term, but we have a whole lot of such terms, limit as delta omega goes to 0. Since this integral is viewed as a limit of such quantities, the limit of such quantities can also be viewed as an integral. This will be equal to 1 over 2 pi from minus infinity to plus infinity of h j omega times x j omega e to the power of j omega t d. And we observe that this is in the very form that we have for an inverse Fourier transform. So, if the response of this is y of t, then this can be written as this is your y of j omega. Therefore, y of j omega will be, if this is y of j omega, then this will be equal to y of t. Therefore, y of t which is given by this quantity can be thought of as 1 over 2 pi minus infinity plus infinity. This is y j omega e to the power of j omega t d omega. So, that means y j omega, if this is the inverse Fourier transform of y of t, y of j omega must be equal to this. So, the conclusion is that the Fourier transform of the output quantity equals the Fourier transform of the input multiplied by the system function. So, this is a very important rule. The Fourier transform of the output, the general system here y of j omega will be equal to the Fourier transform of the input multiplied by the system function h of j omega. Now, one point is we have been talking about the forced response, the particular integral solution, and we will explain later that this is indeed will be the total solution because including the transients. So, for the time being assume that this is so. I will explain that in a little later point of time why it is so. So, we can say that the output will be equal to the input Fourier output Fourier transform will be the input Fourier transform multiplied h of j omega, or h of j omega can be thought of as the Fourier transform of the output to the Fourier transform of the input with 0 initial conditions. I will talk about that later with 0 initial conditions. Initial conditions. So, this is another way in which we can find out the response of a linear time invariant continuous system for a given excitation or the given input. All you have to do is from the given input find its Fourier transform. You know, calculate the system function or determine in whatever manner you have at your disposal. Multiply these two, that will give you the Fourier transform of the output. Find out the inverse Fourier transform, that will give you the response quantity. That is how it goes. One more property of this system function is if the input happens to be a delta function, a unit impulse, then we know that x j omega equals 1. Therefore, the output Fourier transform y j omega equals 1 multiplied by h of j omega. That means, the impulse response if I call impulse response h of t, that is the inverse Fourier transform, because under an impulse excitation the output has a Fourier transform h of j omega. Therefore, the time function corresponding to this will be inverse Fourier transform of h of j omega. Or to put in other words, the impulse response h of t and the system function form a transform pair. This is indeed a very useful result. System function is the Fourier transform of the impulse response, or the impulse response is the inverse Fourier transform of the system function. Now, this idea ties in nicely with our convolution property. You recall that earlier I mentioned that in our introductory lectures, I mentioned that the output can be thought of as the convolution of the impulse response and the input. So, you recall that we said output y of t is the input x t convolved with the impulse response. And from the Fourier transform theory, we know that when you have two time functions convolved, the Fourier transform is obtained by taking the product of the Fourier transforms of the two functions which are convolved. So, that is exactly what we had here. A y j omega is h j omega times x j omega, this is equal to this. So, these two go in together. Right. Now, with these basic concepts relating to a general system, let us apply these techniques. Let us apply this to a electrical network problem where we would like to calculate the output for different types of excitations. Let us now apply these concepts to evaluation of the transients in a particular network through an example. Now, what we are really doing is the given excitation input function is thought of as a number of elementary sinusoids lasting from starting from minus infinity and extending to whatever point of time at which we want to evaluate the response. Now, if a sinusoid is given as an input to a network, the forced response is also a sinusoid, and we are trying to find out the summation of the forced responses to the individual sinusoids. Now, let us see, if the system does not have any initial energy to start with, we will assume all capacitors are uncharged, all inductors do not have any zero current to start with, any non-zero current to start with, then all these sinusoidal inputs will give corresponding sinusoidal responses, and we would like to add them up, and that is what we get by finding out y j omega as h of j omega times x of j omega, where x of j omega, h of j omega is the system function which is obtained under steady state sinusoidal conditions. Now, in a differential equation, we have both the complementary solution and the steady state solution, which is steady state solution being the particular integral solution. Now, by adding up all these elementary responses, we are adding up all the forced responses or the particular integral solutions that we have from these various input functions. Now, what about complementary function? Since we are starting our time, the application of these inputs at t equals minus infinity, and if the system has got a natural response which dies out with time, which has got the natural response modes have negative values for their real part, that is natural frequencies have negative real parts, then what happens is starting from minus infinity they decay down to 0 when we are talking about the response, calculating the response at finite time, particularly from t equals 0 and beyond, and therefore, all the natural responses would have died out, and what we are now dealing with is only the forced response. That is why the total response is obtained by adding up the forced responses of all these elementary sinusoids which have started from minus infinity and continued maintaining their amplitude right through the period up to plus infinity. The natural responses would have died down. This is true of all systems whose natural responses decay with time. There may be certain difficulties where the natural responses do not die out with time. If the natural responses of a system, natural frequencies have 0 real part, that means they have sinusoids or DC responses as natural responses, then there will be some problems, but we will not be dealing with such cases as far as this course is concerned. We will assume that the system has a stable system with all the natural responses being decaying with time in exponential manner, and then because they have started at minus infinity, by the time we come to 0 they have decayed down. And it can also be shown that the inverse Fourier transform of the response function through contour integration in the complex plane, it can be shown that suppose you want to apply the excitation at time t equals 0 and then want to know the response from t equals 0 onwards for positive t, that means the function has the excitation is 0 for negative t, and we would also like to have the response also 0 for negative t because it is a causal system. And if you take the inverse Fourier transform of y of j omega, it turns out that for such systems as we have studied, the response for negative t is going to be 0. Therefore, this is quite in accordance with the causality principle of the system, and therefore, there is no necessity for a natural response terms to appear in the final solution. So, the overall to sum up then, if you apply the Fourier transform theory and then apply the steady state methods, after all h of j omega is the response, is the ratio of the response to the input phasors under steady state conditions. So, we are applying the steady state theory and apply and obtain the natural the total transient response, even though we are applying steady state theory, because all the natural responses add up to 0 for negative values of time, and they decay by the time we start counting our responses. We are taking account of the responses for positive t and beyond. So, let us take an example to illustrate this. Suppose I have a current source IST which is given to a circuit like this, where this is a 2 ohm resistor, 1/6 farad capacitor and a 1 ohm resistor, and this is my output that I desire. And I would like to so this can be viewed as a system where Is of t is the input and V naught is the output. So, from steady state theory we would like to find out what is the h of j omega for this. What is the ratio of the phasor for V naught to the phasor for I s? So, V naught phasor over I s phasor under steady state, under sinusoidal steady state. This is our h of j omega, because once you identify this as the output and this as the input, we have the output to the input, the system function can be defined V naught over I s. You can work this out and show that this is equal to j 2 by 3 omega divided by j omega plus 2. Using the concept of impedances and admittances, you calculate the ratio of this phasor to the input phasor, that will be what it is. So, this is the system function. So, once we have the system function, we can calculate the response to any kind of excitation I s of t that you have. We assume that the capacitor is initially uncharged. So, let us take first a case where I s of t is a delta function. Then the input is a impulse function, therefore, the input, the Fourier transform of the input equals 1. Therefore, the output Fourier transform V naught of j omega equals the system function, which is equal to j 2 by 3 omega over j omega plus 2 times the input Fourier transform, which is equal to 1. And this I can write this as, now I have a function like this, I must find out the inverse Fourier transform. So, I must put this in a recognizable form. So, this I can write this as 2 upon 3 minus 4 upon 3 over j omega plus 2. This is what we will call a partial fraction expansion. We will talk about this in greater detail when you go to Laplace transform, but you can easily see that this is equivalent to this. I try to break this up into two parts, each of which can be recognized to be the Fourier transform of known functions. That is the general idea. Therefore, V naught of t is obtained as 2/3 in the transform domain. Therefore, in time domain it is 2/3 of delta t, 2/3 of delta t, and the Fourier transform of that is 4 upon 3 e to the power of minus 2t ut, because 1 over j omega plus 2 corresponds to e to the power of minus 2t ut, and you have minus 4 upon 3 as the coefficient. So, this is the total response of the system when the input is a unit impulse. Then a second case, suppose I s of t is a ut, then I s j omega, the input Fourier transform, is 1 over j omega plus pi delta omega, and the output V naught j omega is 1 over j omega plus pi delta omega multiplied by the system function, which is j 2/3 of omega divided by j omega plus 2, and you can simplify this and show this to be equal to, you see, pi delta omega multiplied by this becomes 0, because this whole function is 0 at omega equals 0. Therefore, this does not contribute to any term in the final result. This will turn out to be 2 by 3 j omega plus 2, or V naught of t equals 2/3 e to the power of minus 2t ut. So, that is how you can calculate the transient performance of a network using the Fourier integral and Fourier transform concepts. To summarize, in this particular lecture, what we have done is we started out with the formula for integration, and we saw how the integration rule is compatible with the differentiation rule. In particular, we said any function f of t integrated from minus infinity to t is equivalent to multiplication in the transform domain by a term 1 over j omega plus pi delta omega, and in particular when the transform f of j omega is 0, when omega equals 0, the second term drops out. Then we saw how the Fourier transform theory can be applied to general system studies, and in the general system studies the frequency response function h of j omega plays a very important role as far as Fourier transform theory is concerned, and h of j omega is the value of the phasor of the output to the phasor of the input at the particular frequency. So, under using steady state methods you can evaluate h of j omega either experimentally or through analytical calculations, and once you have h of j omega, the output Fourier transform and the input Fourier transform are related by the system function h of j omega. And I mentioned that even though this is the ratio of the forced response, the Fourier transform of the forced response to the Fourier transform of the input, in many particular cases, many cases which are a common interest where the natural frequencies decay, natural response decays with time, this also gives me the total solution, gives us the total solution. And we took up a specific example to illustrate this idea, and we took a RC network and found out the response of the RC network, response in the sense the output across two terminals is calculated for two different excitations, one an impulse excitation, the other is a step excitation. And this shows that the Fourier transform theory can be applied to evaluation of the transients in networks, not even though the Fourier transform is essentially related to steady state behavior of networks, it can be made use of to evaluate transients as well.